Lynn Warburton. I'm the research leader of the Western Regional Plant Introduction Station. We're also called the Plant Germplasm Introduction and Testing Research Unit, part of the National Plant Germplasm System. So we're based on the Washington State University campus here in Pullman, Washington, and we have over 100,000 different populations, cultivars, genetically distinct groups of seeds or plants. And those 100,000 different things are split up into 5 curatorial programs, which include the horticultural crops, which are lettuce, garlic, sugar beets, medicinals, ornamentals, bunches of other stuff, agronomy and safflower. So those are all of the grasses that grow in cooler season areas of the United States. We have the cool season food legumes, which are peas, lentils, chickpeas, some other related protein producing species. We've got the temperate forage legumes, which are the alfalfas, clovers, and related species. And we have the bean collection, the Phaseolus collection, which just by itself encompasses 18,000 different kinds of beans. So we have huge genetic variation within our collections, in addition to all of the cultivated and domesticated, including the landrace and farmers varieties. We have wild species, things that are related to the crops that we hold, and also a bunch of economically and ecologically important native species. So we are one of the largest and one of the most diverse collections in the United States, and we support all of the cool season farming, breeding, production, food, basically, in the cool regions of the United States.
My name is Alex Cornwall, and I am the curator for the horticultural and beta crops collections. Beta is sugar beets, and then horticultural is pretty much everything else. So right now we're in the allium collection for garlic and some ornamentals and wild species. It is all a clonal crop, which means that it does not produce seed. Our collection does not include the onions or the green onions because they produce seed and are housed in another facility. So we have over 300 different types of garlic, as well as 10 ornamental species that we keep in this field. The collection itself has probably another 20 more different species, and most of those produce seed. But in here, we have to keep our numbers high. So each plot has 35 different cloves planted every year. And that's to keep our survival and keep those numbers up so that when people need it, we have what they need. So every year we have to dig and harvest our bulbs in the end of July. And after that is when we let it cure in our dry shed. And then we clean it, cut off all of the scapes and the flowers, and then break it into cloves, some of the bulbs into cloves, and get that planted in early October so that we can have that regeneration, because garlic needs cold. It needs to be cold in the winter so that it can form nice, healthy bulbs. Within our collection, we include the entire lettuce collection, or Lactuca, and that consists of about 26 different species of wild, and then our cultivated lettuce, Lactuca sativa, is what we generally eat. And there are 5 to 6 types, depending on who you ask, of different types of lettuce that you can get. So there's iceberg lettuce, romaines, leaf lettuce, there's stem lettuce even if you want to look that up. But so our collection is about 2,300 different types of cultivated lettuce, and this field is our yearly increase. So we can only grow about 70 accessions a year, and mainly that's because we need to prevent them from crossing, and we want to contain the biodiversity that we have in each accession. And so at this stage, they're still growing, and we will take data on them so that we can have that for our database. And then from there, we will put cages on to prevent pollinators from coming in and out. So lettuce seed, it's important for us to grow this around every 15 years if we can, because lettuce has a very high oil content in its seed, and which causes it to go bad quickly. And 15 years is about when it starts to decline. And so we need to regenerate it sooner than later. So a lot of lettuce species are distributed across the world, but here in North America, we have 5 different species that are not well conserved in our gene bank. And so I'm working on going through and collecting with my technicians to go find these native lettuce seeds and add them to our collection so that we can conserve our native biodiversity as well as our cultivated.
I'm Paul Gillespie. I curate the temperate grass collection here in Pullman, Washington. Today we're touring one of many fields and looking at the diversity of temperate grasses. Temperate grasses differ from warm season grasses because they are C3. The C3s are really predominantly perennial and require a vernalization period. Therefore, this temperate cold winter provides that, and we can care for the diversity of grasses here in Pullman. So a lot of these grasses are from Eurasia and other grasslands around the world, but we do have a lot of natives, and these western states are really a great source of genetic variation for some of these grasses. We do our best to conserve grasses, but they are very diverse, very complex, and there's inherent challenges with resources, infrastructure, and just managing such a large collection. There's about 27,000 accessions, about 60,000 inventories of grasses, and that's a lot to deal with. In the temperate grass program, we deal with outcrossing species, and that becomes problematic because we have limited space. The method we use for pollination control is isolation by distance, so no accession of the same species is within 150 feet of another. We have 1,200 species in the collection, so that's not a huge problem, but we are limited on space for specific accessions. I can think of the fescues, for example, that we have about 500 fescue accessions and really not enough space to grow them all out at once. So these seeds were started in the greenhouse, transplanted mechanically, and then pretty much everything else is done by hand. We hoe within these grass plots to limit weeds and contamination. We cultivate within rows, and then when everything heads out and there is mature seed, we come in with a sickle, probably 10,000 year old technology, grab these seed heads and then put them in a bag. We dry them out and then take them to seed cleaning, and we have a seed cleaning team that processes all the seed and returns it to the seed bank. Grasses fill quite a few important roles in the economy. They support whole industries and other agricultural economies, such as turf, forage, as well as they support a lot of wildlife. So if you're a hunter, generally what you eat is eating grasses. So grass conservation is important on many levels, and one is grasslands. Having these really productive whole ecosystems really that can regenerate soil, build soil health, is really fascinating and really important for our future.
Hi, I'm Britton, and I work for CSFL, which stands for Cool Season Food Legumes. The crops that we work on are things like chickpea, lupin, faba bean, pea, and lentil. And some of the ways that we collect the data for these crops are high throughput methods. So we have a display here of some of the equipment that we use to collect the data in the field. These two are UAVs, so we can fly the field and we collect images with these RGB sensors. And then here we actually have a newer machine that we're just starting to use. It's a rover, and it has a lot of camera sensors on it, as well as 2 LiDAR sensors. So a lot of the data that we collect with these UAVs and this rover, important trait data like biomass and plant height, the data actually gets put into our GRIN database, and then breeders or plant researchers can access that data, and it can help them inform their breeding projects. So we take a lot of data on wild crop relatives and crops that aren't so domesticated. So for example, if a breeder wanted to work on forage quality, our biomass data and plant height data from the UAVs would be a really good starting place to do some screening of the collection and help them make informed decisions for their breeding programs. So this is our screenhouse facility. We can regen about 42 accessions of peas per year. And to give you some perspective on that number, our collection of peas is over 6,000 accessions. So it takes a lot of years to be able to grow out everything in the collection and get high quality seed back. The screenhouse is a semi-protected facility, so we don't get as many pests in here. We're not out in an open field. We're protected from wind and rain. So we get really high quality seed from this house. Each line is a different accession of pea. So this is a really cool place to see the variation in Pisum, because you can just see physically there's a lot of variation between each line. So we have our more cultivated white flowered lines. On this side, we have pigmented flowers, which is typically an indication of a less cultivated variety. So this is Pisum sativa maladius, more in the wild realm of peas. They have a really strong shattering trait. So as soon as they mature and their pods start to dry down, they will shatter, which requires constant supervision. So to harvest this accession, we will basically come in every morning and check to see if the pods are dry enough to harvest and put into a harvest bag. If we miss them for a few days, we'll lose a lot of seed. So a really cool plant, really good wild crop relative diversity in our collection, but also high maintenance. This pea accession here has kind of a unique trait. It has fasciation stems. So the stems are kind of growing thick like straws. And what it creates is this cluster of flowers at the top, which is really unique for peas. So this would just be an example of a trait that we would consider important because it's different. Another thing about this particular accession is it has the normal leaf type for peas. So we have the stipule at the stem, 2 leaflets, and then tendrils. And interestingly enough, if we go one accession over, we have a pretty rare mutation, which is called an acacia leaf type, where there's no tendrils and there are leaflets all the way down, which is really pretty to look at, but not so great for training the plants because they don't have anything to grab onto. And then our last major leaf type, one accession down, is the aphylla leaf type, where all the leaflets have been modified and are now tendrils. So this is a really good mutation for resistance against lodging, because the plants will actually support themselves and all kind of stand up together, making harvest a lot easier in the field. And so we just have a really great variation out here. Our primary job is to get high quality seed, but as we're doing that, we also take trait data all the way through. So when they're flowering, we take images, we measure the flowers, we take color data, we take plant height data, we take pod data, we take yield data. So as we're growing the regenerations for the collection, part of our job is just to make sure we have a huge high quality data set along with that seed. Again, just as a resource for plant scientists and breeders as they want resources for their programs.
So the Prosser-based Temperate Adapted Forage Legume Program, that is a mouthful, but it's crops like alfalfa, cultivated clover, and trefoil, and again, many other wild relatives are maintained in the collections here. The collection's about 250 different species in 3 major genera, Medicago, Trifolium, and Lotus. I think it's just over 13,000 unique accessions, and these are all forage legumes. And this germplasm, again, is mostly introduced from Central Asia, where the collections were made, some of them over 100 years ago, and they're maintained. The information and the collections themselves are made accessible to our stakeholders. Stakeholders include plant breeders in academia and public institutions, public research, nonprofit, but also stakeholders from the private industry access the germplasm to mine the collections for traits, traits for disease resistance, insect pest resistance, biotic stress tolerances. So with regeneration activities, this is something that starts early in the season by selecting germplasm that needs to be regenerated. And we queue germplasm based on the seed quantities in particular, but also viability. And once they've reached below a certain threshold on viability, we queue them for regeneration. We receive seed from Pullman, and in February or so, we plant in greenhouses the seed. A few more months of growing in the greenhouses, then they are brought out to our field cages. And we put about 100 to 150 transplants in each of these cages. We use drip irrigation. Everything is labeled accordingly. And as the plants are established and before they begin to flower, we put these insect-proof cages over them. And then we introduce managed insect pollinators. That's in order to maintain the genetic integrity of the accessions that we are regenerating seed for. And it's critically important to prevent possible incursion of a transgenic trait into the field regeneration cages. That's because we distribute seed to folks that are expecting seed that isn't transgenic. And this is one of our sentinel plots for alfalfa. We manage this plot without a cage, and we let natural pollinators come to it and potentially bring transgenic pollen from commercial alfalfa that is grown nearby to pollinate and fertilize the flowers. We would then harvest this seed at the end of the season and test those seed lots with immunostrip assays for the presence, the adventitious presence of the transgene. And we're talking about the glyphosate tolerance, the transgenic trait or Roundup Ready trait in alfalfa. We have regeneration cages close by, and we're just wanting to know if there is any adventitious presence or pollen moving into the field site, potentially impacting our regeneration activities. We alternate field sites, and we picked this field because alfalfa hadn't been here for like 5 or 6 years. Come to find out that we have some volunteer alfalfa seedling plants, and we have treated this field with the herbicide glyphosate, and we didn't kill these seedlings, and it was a surprise to us. And that's because these are transgenic. Likely a mother plant fertilized some seed. These seeds had fallen and got incorporated into the ground. We did some tillage. We moved the seeds around, and all of these seedlings happen to be transgenic. And it could have been a really big problem. None of the cages that we have contiguous here are of alfalfa, but we have some alfalfa in the same field site, and we wouldn't want some of these volunteers in the middle of one of our field regeneration cages.
Hi, I'm Sarah. I'm the bean curator here in Pullman, Washington, and I manage the bean collection. So our bean collection, the USDA bean collection, consists of over 17,000 accessions, and it's primarily made up of the 5 domesticated species. So that's your common bean, which includes string bean, pinto bean, navy bean, kidney bean, all the same species. And then related to that, your lima bean, Phaseolus lunatus, a tepary bean, which I'm standing next to. That's a Acutafolius. It's a drought-tolerant, heat-tolerant bean native to southwestern United States. Coccineus, or scarlet runner, it's often planted as an ornamental in the United States. It has large seeds called giganti in Italian restaurants. And then Dumosus, which is a hybrid of common bean and Coccineus. In addition to those 5 domesticated species, we also have 51 wild crop relatives that are related to Phaseolus. Right, and so we're excited about maintaining those because they could potentially be used for breeding in more stress tolerance to our cultivated types, or potentially being domesticated on their own. And we have wild species from South America, Central America, and North America. All right, so the way that we do regenerations is all entirely in the greenhouse for a couple of reasons. One is to prevent the spread of bean common mosaic virus, which is spread by aphid. And then 2, because beans are a tropical crop, many of them evolve near the equator where there tends to be 12 hours of dark. And here in the northern latitude, we don't get those long nights until late summer. So we don't get flowering until September, and you don't get seed until after the first frost. So to overcome that photoperiod problem, we do regenerations here in the winter in greenhouses. We have greenhouse space combined at 2 locations for 380 accessions to be growing at one time. Something else that we're working on that we're really excited about, because behind that that photoperiod sensitive wall, there's a lot of genetics for heat sensitivity, increased nutrition, other environmental stresses. And so we do some pre-breeding where we'll do opportunistic crosses where you cross a variety that's photoperiod sensitive but might have improved stress resistance with a common commercial variety so that you get the best of both worlds, a bean that's easy to grow with increased stress resistance. So that's something else we do that's a lot of fun. Collecting characterization traits in the greenhouse is incredibly challenging because the greenhouse growing environment is quite different than a field growing environment. And so two of those traits that are really important to growers and breeders are plant maturity time, and so from seed planting to flower formation to seed harvest, right? And that is dependent on how much heat, how much light, how much nutrition the plant has, but also on the day, the photoperiod. So how long the day is, how long the night is. And because we're growing them in the greenhouse, all of that is, we're making the right environment for them. So we don't have an accurate idea of how long it would take to mature in the field. So we need to do that. So one is plant development in field conditions. And then the other one is growth habit, which is it a bush, is it a climbing vine, or is it a prostrate vine? But in the greenhouse, you can force any of them to grow up a trellis, and that's what we do just to keep the greenhouse clean. But that's one of the phenotypic traits that is actually kind of hard to record when you're growing in the greenhouse. And so that's partly why we're trying to reestablish field characterization plots here at Pullman, and then also work with community growers to get them to trial some of our bean varieties and get characterization notes at different growing environments. You can see that some of the rows aren't fully planted, and that's simply because we didn't have enough seeds to fill the whole row. So if we have less than 15 seeds, which is about the number of pots that we have, I'll only pull half of the seeds from the cold room and plant them, just in case we have a greenhouse catastrophe. A tornado, steam failure, something like that might happen, and then we'll lose 7 plants, but we'll still have 7 seeds in the cold room to regrow. You'll also see that in some of the rows, we don't have plants growing in every pot. There's a significant portion of our collection has low vigor and viability, and potentially even just dead seeds. I was looking in the collection, and 40% of our collection is over 30 years old, or we don't know how old it is. So maintaining seeds for that long is hard. Okay, so we choose the most vulnerable seeds to regrow so that we have healthy seeds. We plant a row, we hope it flowers in the greenhouse conditions and light regimen, heat, everything like that. And then as pods form, we pick mature pods off, we let them fully mature on the plant, harvest pods into bags. Unless it looks like the row is going to have a ton of pods, then we'll harvest the whole row. But we always keep the bags at the end. One, in case we only have a few, hand harvesting gives higher quality. And two, if we have pod shattering. So for our semi-domesticated plants, as they mature, they throw their seeds. And so we need to be able to come in and pick the seeds as they mature. This is kind of our quarantine space. So our beans that are showing virus symptoms, we put in here. So we know that some beans in our collection have bean common mosaic virus, which is a seed-borne podavirus, but the plants can live with it and not all the seeds inherit it. So for those successions that we have only a few seeds left of, if they're showing virus symptoms, rather than roguing out the plants, we actually grow the plants, collect the seeds, mark them as having virus, and one day when we have more capacity, we will clean them up and then make them available.